Okay, so these next reactions we're going to do are going to be similar to what we've been doing, except that we're going to do them with conjugated bonds. So this is going to be addition reactions to conjugated alkenes. Okay, so let's first just do a little bit of double and pi bond terminology. So we remember that if we have this is going to be conjugated. We know that here we've got a series of sp2 hybridized atoms. And it doesn't have to be sp2. We could also have sp, but what we can't have is sp3 hybridized, because once we have sp3 hybridized, we don't have that system of unhybridized p orbitals. So the unhybridized p orbitals they're either going to be involved in these pi bonds or in resonance with a lone pair or something like that. And these are going to be what allows this to have communication across those unhybridized p orbitals with these 4 pi electrons. So here we have 1 pi system with 4 pi electrons. And this alternating double and single or pi and single bond setup is what we call conjugation. All right. And we remember that when we have conjugated systems, what happens is that we get the stacking in of the pi orbitals. So we'd have like a pi 1, a pi 2, and then the pi 3 would be antibonding. The pi 4 would also be antibonding. And here we have 4 pi electrons, so we would fill up those 2 bonding orbitals. And as we add conjugation, that makes that gap smaller and smaller, decreases the delta E there, and tends to eventually get us into compounds with colors, because the energy gets small enough to be within the visible region. Most organic compounds, the energy gap is more in the UV region. We can also have a system like this where we have 4 pi electrons total, but we have 1 pi system here and 1 pi system here, because this carbon atom here is sp3 hybridized, and this basically tends to work as an insulator and insulate these 2 pi systems from each other. And so these are going to be 2 isolated pi bonds. Now, what happens here is that these are going to have very similar energies. These particular ones would not have identical energies because they are, a little bit different. One is terminal and one's internal, so that's going to be a little bit different setup. But you'll have orbitals that look a little bit more like this, where these 2 orbitals are similar energy. Usually if they're the same energy, we'll call them degenerate. But effectively, this sp3 hybridized atom is going to act as a stop sign for electronic communication. And, these molecules, if we have a long system of these unhybridized p orbitals where electrons can sort of flow, we can end up with conductive materials in this way. Similar to our conjugated system up top, we can have a carbonyl as part of a conjugated pi system. So here, this is going to give us still a conjugated system. And we see this in our our weakening of the carbonyl bond and the lower energy stretches that occur when we have conjugation with a carbonyl, for example. So this is still going to be 1 pi system. with 4 pi electrons. Okay, we can also have cumulated systems like this. This can also be represented by a dot in the middle. So these would be called cumulated. These would have 2 distinct pi systems because these would have to be perpendicular with each other, with having the same carbon atom having a pi bond on the right and on the left. That means one of those pi bonds is kind of going up and down. Maybe we'll pretend like the one on the right is that one. And then the other one is going to be coming in and out of the board like this. Okay, so this would be 2 pi systems with 2 pi electrons each. If we have another system like this, okay, here we do have a conjugated system with these 2 pi bonds over here on the left, and then one of the pi bonds from the alkyne. So we have one conjugated pi system that has 6 pi electrons, and then another one isolated pi system with 2 pi electrons. And it's for a similar reason in that the carbon atoms on the alkyne are involved in 2 pi bonds. And so those 2 pi bonds are orthogonal to each other or perpendicular to each other, and they do not overlap. So that means that one of those pi bonds is going to be not in the same plane as the rest of the pi bonds. Okay, so getting back to reactions, let's think about what can happen when we have the addition of HX to conjugated systems. Okay, so the simplest example here and the most preferable one, honestly, because it can get a little ugly when we get too much substitution going on. There's too many possibilities for products. This would be called butadiene. Okay, because we have 2 alkenes and we put the A back in because of this hard consonant here. And if we're the technical name, if we were putting in the numbers, would be buta 1,3 diene. And we're going to add HBr to this. Okay, so I'm going to leave this without the products for now, and we're going to come back and fill those in a minute. Okay, so let's go through the mechanism here. Okay, partial negative, partial positive. We know that the first step of these addition reactions is going to be that electrophilic addition step. Now here we have 2 pi bonds to choose from for the attack. But thankfully, because it is 1,3-butadiene and it's so simple, effectively they're both identical. So it doesn't really matter. We're just going to pick one. Now, if they were distinct, then unfortunately you would need to draw both possibilities. And that's why I said we're keeping it simple and doing it this way. All right, so I'm adding this. And let's go ahead and draw in our other atoms to keep track of everything around the reaction site. And I'm going to go ahead and change the color of the HBr. So again, like before, we're going to put that proton on the less substituted carbon because that allows us to have a more substituted carbocation, which is what we want because that's going to be more stable. This would be a secondary versus if we put the H on the other atom, which would give us a primary. Also, notice here that we have resonance. We have the allylic cation pattern here with the pi bond next to the atom with electron deficiency. Okay, so we're just going to draw the other resonance structure here. Okay, now here we see this one is secondary and this one is primary. So obviously the secondary would be the more stable of the two intermediates. However, the fact that we have resonance basically means that both of these are stabilized because what the resonance hybrid would look like here is that we would have a partial positive on both of these carbon atoms. Okay, so that's going to be favorable for both of them. All right, so then the question might be asked, which one of these positively charged carbon atoms is the one that the nucleophile is actually going to attack? So let's take a look at the two possibilities in terms of the products that we would get with these two different atoms. All right, I'm going to make an attempt to copy this over to the next page so that hopefully I don't have to redraw it, but I don't know that that's going to be the case. All right, I'm going to have to redraw this on the next page, and that's okay. So I'm going to draw these two carbocations, and then we're going to look at what happens if each of them gets attacked. Okay, so if the bromine attacks here, then the product, so this would be the coordination step, would be this. And of course, the bromine can attack top or bottom, and that is a chirality center. So it's either going to be top or bottom, and we would get both. Over here on the left, if the bromide anion attacks there, again, a coordination step. Okay, so looking at this, this intermediate here makes the most sense because it's a lower energy intermediate. Okay, so this is the lower energy intermediate. However, and this would therefore be the higher energy intermediate. Because this is secondary and this is primary. But if we look at the two products and we think about the alkene substitution patterns here, this alkene would be mono-substituted alkene. Okay. And this one would be the di-substituted alkene. Okay, so this one would be the lower energy product. And this would be the higher energy product. Okay, so if we draw this out in terms of the energy diagram to kind of look at where things are, I'm going to go ahead and put labels on these different intermediates and products. I'm going to call this one A, and this one B, and this one C, and this one D. So we don't have to redraw the structures on the reaction diagram. Okay, so here I'm going to draw A to B in purple. So both of them are starting out at the same place with the same substrate. Now, A is going to give me a lower energy intermediate than C. Okay, so this is A and this is C. All right, so that first step to get to A is going to look something like this. And then the first step to get to C is going to look something like this. So if we're looking at the delta G double dagger, the transition state energy, then the one for A is going to be much smaller than the one for B. Okay, now then if we keep going and we look at the products, B is less stable. So B might be like here, but C is more stable, so C might be down here. All right, so let's draw these arrows, or draw the curve, finishing this out. Okay, and then this one would go all the way down here. Okay, so that means that for the blue pathway, we have a higher energy intermediate, which means it's going to take more energy to get there. We would need more thermal energy, more pressure, more something to get us up over that higher activation energy barrier. But then the product is more stable. So that means if we can get there, then that's going to be more thermodynamically favored. The purple pathway has the lower energy intermediate. So it's easier to get there, but then the product is less stable. Okay, so that means that if we go at a lower temperature, we're going to get the purple pathway, and we're going to get product B. If we go at a higher temperature, we'll be able to overcome that higher activation energy barrier and get to the more thermodynamically stable product. So the blue pathway is what's called the thermodynamic product. And the purple pathway is what's called the kinetic product, because it'll form more quickly because we have that lower energy. So going back to what we looked at here and drawing the products out, so this is one set. This would be the thermodynamic product. And then the other set, this is the kinetic product. This one, the thermodynamic product, because we added to the two atoms that are beside each other, this is often called the 1-2 addition. And the one on the right, because we ended up effectively adding to the 1, we're adding a hydrogen to the 1 and the bromine to the 4. This is often called a 1,4 addition. And the 1 and the 4 and the 1 and the 2 don't reflect necessarily the numbering that you're doing in the naming. Sometimes it is, sometimes it isn't. It's more just the positions of the atoms that are getting reacted with respect to one another. So looking at the diene itself, the kinetic... Sorry, I made a mistake. Let me go back and fix this. This is the kinetic product, and this is the thermodynamic product. So the 1,2 addition, because it is lower energy intermediate but less stable product, that's kinetic. And the thermodynamic is more stable product but higher energy intermediate. So again, the kinetic is going to be favored at low temperatures. I'm going to put low in quotes here, and then the thermodynamic is going to be favored at high temperatures. And the reason I'm putting these in quotes is because, the high and low is relative. You'll often see, to get the kinetic product, we actually have to use extremely low temperatures. You might even see like a negative 78 degrees C or something along those lines for the kinetic product. And that would be to obtain that in the lab. What you typically do is it's a dry ice acetone bath. So you'll take acetone and you take dry ice and you crush it up and you add it slowly to the acetone until you get like a slush, and that gets you to negative 78. And so that's a temperature that's easily obtainable in the lab. So you'll see that temperature used quite a bit. And then for the 1,4 addition, with the high temperatures, you're probably looking more like at room temperature or something like that. So you'll often see 25 degrees C associated with those types of reactions. All right, so looking at actual percentages for this at different temperatures, let's look at an example. Let's say we're adding HCl at 20 degrees C. We'll get about 25% of the product will be the mixture of the two 1,2 addition product. And then 75% will be the kinetic product. Sorry, the thermodynamic product. I keep doing that. The 1,4 addition product. Okay, so this is our higher temperature with this. If we use a lower temperature like that dry ice acetone bath, then for the 1,4 addition product, we tend to get around 20% of that one. And for the kinetic product, the 1,2 addition product, or I guess the mixture of those two enantiomers, we tend to get about 80%. So again, this is the kinetic product. This is the thermodynamic product. And then here, this is the thermodynamic product. And you see at the lower temperatures, we get less of it. And then this is going to be the kinetic product. And at lower temperatures, we tend to get more of that one. Okay, so that is it for these reactions. Similar things would happen, with other substrates. Sometimes, again, because you might have more substitution on the molecule, you might get a lot more products, so it can get pretty complicated pretty quick.